Yes, so let's do like a quick recap of session 4. So we wrote a whole smart contract from scratch, like a counter contract. We have some different methods, like a get counter, increase counter, decrease counter, reset counter, set counter. And, along the way, we learned how to turn a module into a smart contract using the startnet contract attribute. We also learned how to handle the storage of the smart contract with the storage struct, with the proper attribute, and then with the methods that are part of the trade as well, to write and to read from. We learned how to configure a smart contract during deployment with a constructor, right? If you remember, that's why we pass the initial value and who the owner of the smart contract is going to be. We also learned how to define and emit events. Every time we made a modification to the counter, we emitted an event, basically explaining the reason of the change. So any indexer can pick it up and other apps can react to it. We learned how to interact with other smart contracts using the dispatcher. And if you recall, the dispatcher is something that was derived from the interface that we defined at the very top. And we learned how to call the smart contract. In this case, we call the STRK token smart contract, is the ERC20 token. And of course, I show you how this dispatcher came to be. It came from the trait we defined at the top as the interface. So the compiler took care of creating the dispatcher for us based on the trait. We also saw how to revert a transaction with an error message, right? And this was the underflow protection that we defined. Whenever the counter trying to go below 0, we actually show you how to throw an error with an assert, and that will in turn revert the transaction and show the error message as received. And finally, we learned how to use a component from OpenZeppelin. This case was the ownable component, and I show you how to actually connect all the different parts, how to connect the component to your storage, to your event, and how to use it internally as well. That was session 4. Now, session 4 today, we're going to start talking about manual versus automated tests, then unit versus integration tests, because we actually did unit before. I'm going to show you how to create your first integration test with Foundry, then more advanced topics like using cheat codes to modify the state or the mocked version of STRK running locally. I'm going to show you how to spy events so we can actually test that the events are being raised correctly. At some point, we're going to have a break. I don't know if it's exactly there, but at some point, 10 minutes. Then we'll come back to show you how to test failing scenarios so you can check that actually some transaction in certain conditions will stop and revert. And also to check for specific error messages when that happen. And at the end, as always, we're going to have a quiz for questions. And that's the topic. So let's jump now. First topic is to talk about manual versus automated test. Give me 1 second to put things into place in my screen. Okay. Let me go back for a moment to the repo that we built last time, right? So that was called, I put it in sandbox. This is the one that we built last session around. And, I was using dev container, right? Because we had this dev container, so it's using Docker in the back. So you can either launch it with dev container, so you click this button and it will launch it in the container, right? As I was doing before. But the other option also, I'm going to show you if I close this. Let me open this again. If you have installed dependencies with STRK, you can skip this step, because if you install with the STRK, you should be able to have everything installed locally. So you should have SCARP, and you should have Foundry as in Forge, which is the binary for Foundry. Right? So I have installed also dependencies with STRK in my system as well. And the other thing that comes installed with the STRK is a package manager for all these dependencies called ASDF. This also comes with the STRK. And the beautiful thing about this package manager is that now you can define dependencies specific to your project, specific versions per project. And you define those versions with this file here called tool versions. For example, this project is defined SCARP 2.11.4, starting at Foundry 0.46.0, and starting at DevNet 0.4.3. So if you want to use these dependencies using ASDF with complete STRK, you simply does ASDF install, and it will install these dependencies for this project in particular. And this way you can skip completely the need for dev container. So today I'm not going to use dev container just to show you the other way with STRK, but you can use both versions. One thing I need to check is that this version is matching whatever is defined in my actual project in the scarp.toml file, contract scarp 0.46.0, yes, and 2.8.4. Okay, they match. That's good. That's important. Okay, so we built this contract last time around. If we go to the counter, this is what we built. And I mentioned we have all these methods implemented. And what we were doing before, to every time we added a new method, was to basically launch. I need to run your install. I think I have to, because before I was in the container, so now I'm outside the container, so I have to install dependencies most more likely. Give me a second. Yeah, so what we're doing before is just to compile the project to start up like a local devnet and deploy to that devnet, start up like a web UI with a debugger, and then in the debugger manually verify things were working. So we're doing something like this, like a yarn chain to start the devnet. It's like a local version of StarkNet, and then with a different console, different terminal, we will deploy it. Which will first compile it and then declare it and deploy it to the local devnet. It will give you the address where it was deployed. And then after that's completed, we were able to spin up the web UI. This is all coming from Scaffold Stark. So at this point, we start up the local web UI. And they should have open now localhost 3000, where you have debug contracts. And this is our, counter contract. This is our contract, okay? So we were doing this last time around. It's not very efficient, it's very slow. So one benefit of today of the automated testing is to actually make a much shorter feedback loop from the time you develop a new feature from the moment you verify that it's working as expected. And we'll do that with Foundry instead of this manual testing method. The other point I want to mention is the difference between unit testing and integration test, because we did cover unit testing before, and that was part of session 3. So if I open that repository, that wait, what is it? It is, it's called Teaching Cairo, right? If let me go to, I've been working on it. Okay. If I open this repo that we created in session 3, you see that we actually have a bunch of tests. For example, if I open, what was the most complex one? Maybe constraints. This was a complex one. You recall we were showing you how to use structs, traits, generics, blah, blah, blah. And then at some point we define our testing suite, right? With this attribute. So this is essentially unit testing. And this is how you do it. And usually the unit test is defined in the same file you define the source code. This works well for functions and things that are like don't have internal state. It doesn't work well for things that are complex and have internal state, like a smart contract. But you can combine both. If I have time, I'll show you how to combine both. But we already covered unit testing, so now I'm going to go and show you how to create actually integration tests with Foundry. So let me go back to the repository we were starting working last time around. Okay, so let me stop this for a moment. The server, the devnet, we're not going to need this at the moment. So step number 1, to create our first integration test, we're going to test something simple, right? We're going to test this function, get counter. Basically, that after we deploy a smart contract, we get back the value we initialized it with. So there's a file called tests that is a sibling of source, and it actually has one file already. It came with some default tests initially that we deleted, so we're going to work on this. I don't like this naming convention using Pascal case because it's more like a snake case is the recommended for Cairo. So I'm just gonna call it like this, change the name, and that's fine. So step number one, I need to find a way to, okay, so let's create the first test scenario. When we have integration tests, we don't have to start by defining this CFG test at the top and define a specific module for it, because now we're gonna have a separate file just for testing. It's not gonna be mixed up with the code for the smart contract. So there's no need for that separation. So we can just go ahead and define a test case. We give it a name, and we're gonna test the first, let's say, test contract initialization. Okay. All right. I'm gonna disable autocomplete again. It gets annoying after a while. All right. So enable we're gonna have to deploy first, to declare the smart contract, then to deploy it, and then to actually read the values. And when we deploy, we pass the arguments for the constructor, which were the initial value and who the owner of the smart contract is. So we're gonna make use now of Foundry for this declaration and deployment. So we are going to import a function called use. It's going to come from smforge std. This is the name of the package for Foundry. And you can see the name because it's defined in the scrap.toml smforge std, right? This is like the library for the binary of Foundry that we have installed. And from here, we're going to get two things: a function for declaring the smart contract and another one for deploying it. Is there a deploy? Declare. Plus. Checking my notes. Oh, it's part of the declare. Okay. So for now, we only need declare from the library. So we can go here. Let's define a new variable. Let's call this is going to be our contract because we're going to declare it. I'm going to use this function. And we're going to have to pass it the name of the smart contract. And we define the smart contract as counter contract, right? So you pass this as a string, counter contract. And then this is going to return, I think it's an option. So we need to unwrap it. There's something wrong with my autocomplete, maybe because I'm using, let me see if I have the extensions installed. So I have the Cairo one. For some reason, this is not showing me. The autocomplete is weird. You know what? I'm gonna relaunch this in the container because I don't know what's happening right now. So to make sure that it's all connected correctly, I'm just gonna launch inside the counter. It's the same. Okay, let's keep going. Let me see what happens if I try to run this test with nothing. So to do that, I open the terminal and just do yarn test. It should say there is no test to be run, but at least trying to find it. Okay, so it's only complaining that there's an unused import there, and it's not finding any contract. Okay, at least everything is connected, so it's fine. This error you see here, for example, plugin diagnostic unsupported attribute. This is just an issue with the way Forge is trying to collect, I guess, all the attributes. It compiles, it works. It's just the issue is that we have a project that has multiple packages in a single workspace, and the scrap.toml is not at the root of the project. So this is something they're working on it to fix. The Foundry team, or I think this is the Cairo team actually, the Starkware. But for now, we're gonna have to ignore this error. It's just a false negative. All right. So back to here, we are trying to declare the smart contract. We get back, I guess it's a result. So we have to unwrap it. And from that, we're going to get back the contract class. contract class. And why this complains? Not found time cheat code contract class. Am I doing this contract class? Let me try again. Dot contract class. Maybe I had a typo there. Okay, so I have the class for the smart contract, so I need to use that for actually deploying it after. So next step, I need to define the arguments for the constructor, right? Because if you look at the counter, if we look at the constructor, it's expected to be passed two values, the initial value and the owner. When you pass values to a smart contract, you always have to serialize them first. You cannot pass them as they are. You can pass them as array or as a U32. They always need to be serialized. And when they're serialized, they turn into an array of fields, essentially. And when you read back from a smart contract, like when you call this get counter, what you get back is also a serialized version of the response that you have to deserialize. That is why at some point you saw that we use STRK. So this is a trait for serialization and deserialization of values. All right. So next step here, we're going to create the constructor array. Constructor argument, sorry. Which, as I mentioned, because it's going to be the serialized version of that, it's going to be an array. For now, let's have it as to be an empty array. Because I'm going to add things to this array, I'm going to make it mutable. Okay. So what is happening here? Type annotation needed. Even if it's an empty array. Let me continue to see what happens next. First thing I want to add is what's going to be the initial count, right? If we see the counter, let's start with the initial count. Let's define here the init count counter. Let's say that I start with, I don't know, 5. And let's say that the, what else do we have? The owner, look at the owner. Right, the owner is going to be an address. So let's say an address is basically a field 252 that gets converted to contract address. We know that a field can also be a short string. Those things are the same. So a common trick to create like a fake addresses for testing is to define the address as a short string that has some value. For example, I can call this like owner. Even though this is not an address, it is a field, and we can turn it into a fake address as well. So to turn it into, let's say, this is going to be the owner address, type contract address, right? So we need to turn the field into a contract address, and for that we use a try into. And that should be it, I think. And contract address, and we need to unwrap it. Unwrap. And of course, we need to bring this into scope, the contract address. So that is going to come from the STRKnet contract address. Cool. Okay, so we have the initializing variable maybe at the top here, and now let's add into the constructor. So to do the serialization, we're going to take, first of all, the init counter. I'm going to call the method serialize. Every basic type has the trait STRK, right? So this is actually this has to be the type U32, so it matches what the contract is expecting. And we're going to pass this a reference to the constructor argument. So what it's doing this is basically it's going to serialize this and it's going to add it to this array. This is how it actually works. So we have now the initial counter. Now we need to also add the owner address, and we do the same thing. So owner address, serialize, and we pass again the array. So it gets added to it. So now this variable contains all that we need in a serialized fashion, so we can pass it now to the constructor. So next step will be to call, we take this contract variable here and we actually deploy contract.deploy. Has this method here. And this method, of course, is expected to be passed the constructor arguments, but it's expected to be passed as a snapshot. So we pass it as a snapshot. So it's like a read-only version of it. And then we do the unwrap, because what we get back from it is now the address where it was deployed. So let's call this the contract address. And they're doing two things, I believe. The second part we don't need, so we put this as just signaling the second argument. We don't really care. And we have some issue. What is it? Unexpected type for tuple pattern missing is not a tuple. Contract address. Deploy, wrap. What am I doing wrong? Contract. Method deploy not found in contract class. Consider importing contract class trade. Oh, maybe we're missing a trade. Yes. So from here, we are missing is the contract class trait, right? Because the trait is the thing that informs which methods you can actually call on the type, right? So this is what's missing to be able to call the deploy. Okay, so we get back the address where this was deployed and something else, and that something else is supposed to be a span. No idea what the span is, but we don't need it. We only care about the contract address. That's what we're capturing the first item of the tuple. So now we have the address, the specific we have confirmation that it was deployed. So we can use the address to create a dispatcher, so we can talk to it and we can call the methods like the get counter, increase counter, all that. And we need to have the interface, the dispatcher, and that is from our contract. So we need to go to counter. Well, first of all, this project is named, let's see, what's the name of the package? We call the package contracts. So we call it contracts. Then we go to the counter module, and then we bring multiple things. One of those is going to be a dispatcher created from this trait, thanks to this attribute, and that's going to be called a iCounter. Is it iCounter dispatcher? Let me see, what's the name of that? iCounter dispatcher. Yeah, and the reason it's not working, it's because to make this accessible outside the module, we need to make it public. Okay? Otherwise, you cannot just bring it. Neither the trait, neither the things derived from the interface at the compile time. So now it's available to be bring into scope. So we can use it, the iCounter dispatcher. And this thing what it expects is the contract address. Missing member contract address, right? So we can say contract address, and then the value is of the same name. And what's happening here? Okay, let's capture this as let dispatcher. Let's capture this in a variable. Missing token. Okay. Everything seems to be working so far. So far, so good. One thing to simplify is that when the name of the property is the same as the name of the variable being passed, you can simplify by just defining it once. It knows that it's just a mapping of the same name. Okay, so this is the same value. So now we have dispatcher. So now in theory, we should be able to call methods like get counter, right? So let's call the method. Let's call dispatcher get counter. But for this to work, we're going to have to bring a trait. Oh, no, it's working. iCounter dispatcher. Oh, because we have dispatcher into scope. That's fine. Okay, get counter. So this should bring us back. How do we call this? Let's get a name. Let's call this. Okay. So let's call this just the let's call it like the current counter, and the type should be. Do we need to call? What's the type of this? What's the type? Unused variable. Yeah, U32, right? So this is the type of the counter, so it's fine. So now what we expect is that the expected counter, the value we expect, should be 5, right? That's what we initialize. So we're just making sure that if we initialize, we get the value back. So now we do an assertion. So we're trying to assert that the current counter is equal to the expected counter. And if not, says initialization counter failed, right? If you get any other value, for example, 0. So this is the first test scenario. Let's see if it's working. Let's run the test. Yarn test. It's going to compile the test suite and the counter contract. As I mentioned last time around, this compilation is a little slow because Scaffold STRK is still using an older version of the compiler. Newer version is much faster, so I actually got in touch with them to upgrade to the latest version of Cairo and Scarp. But for now, we're going to have to make do. Okay, so it found one test, this one here, which was executed. You say the test contract initialization. It tells you how much gas it would use, and it says one test passed. That's great. So it is working. Maybe, let me see. Maybe this is, okay, let's leave it here. It's important that when you have a test, you need to see it fail to know that it's actually working. Let's modify this just to 0. If we do this, this test should be failing. Let me comment this out for a moment. So let's try again. Because if the test failed, it is a good sign that it's actually measuring the right thing and it's not giving us false positives. Any questions so far? Okay, it's running the test, compiling. And you see, right? It failed with the error message initialization of counter failed, which is the message we define here. If this equality is false, and it says, okay, one test failed, right? And this is the one that failed. So this is how you can go back, say, okay, fix the test. So let's fix it. We know it's working. Let's bring it back to what it was. Perfect. So there you have it. This is the first and simpler test. But we need to do a few things too before we start, right? We need to first declare the smart contract. We pass the name. We get back the contract class. We collect that. Then we define all the initial variable for the constructor. We pass the initial counter, the address of the owner. We do here a common trick for testing, which is basically use a short string as a failed, and then we turn it into a contract address. So this is technically the address of the owner of the smart contract. And then we basically serialize these two variables into the constructor arguments. We have to be an array because when you serialize, what you get at the end is an array of fails. So now we pass this or a snapshot of this array. We pass it when we deploy the smart contract. And what we get back is where it was deployed, which address, right? A contract address. So now that we have the address and because we have the dispatcher, we can actually interact with it. We can call it, we can call the methods, we can get counter, and then we verify that the current value of the counter is the initialized value that we passed, and that is the assertion. That is the first test. Any questions so far? Let me see in the chat. Alexander says no. All right. Question. Good. Let's now move on to test something more interesting. And that will be, for example, the increase counter. So we're going to find a new test scenario. Okay. Checking my notes. Okay. So let's call it function test increase counter. Second test case, or second integration test. And of course, every test, you need to deploy the smart contract again before you can test, because you need to start from a blank slate where you have a smart contract initialized the way you want it for your test scenario. Now, I don't want to write this again over and over. So what I can do, I can just abstract this away into its own deploy function that I can call the beginning of each single test scenario. So we duplicate the same logic of deploying. So let's do that. I'm going to call a function here at the top. Let's call this function deploy counter. And it's going to expect to be passed the initial, let's call it the initial counter. right? Because maybe in different test scenarios, we want to initialize the counter with a different value. The owner, I'm gonna hard code the owner. I'm gonna have it to be always the same. I don't see a test case where I want to modify the owner. So for now, I'm just gonna put it here define. So let me do the following. Let's move some of the logic. I'm gonna move all of this here, because when this is done, what I want to return is this dispatcher, right? So every test scenario can actually use it and call the smart contract. Oops. So I want to copy this to paste it here. So now instead of capturing this as a variable, I'm just going to remove the semicolon. So this returns the value directly. Second thing is that instead of having this manually, I'm going to use, actually is init counter. Have the same name, init counter. So I can remove this manually, so I can use the one that is being passed. Let's put this at the top. So they're both together. Okay. This is, I'm going to hard code this for every test scenario. It's going to be always the same, owner, same address. Okay. And return the dispatcher. So now let's make use of this function here at the very top. So we call the deploy counter function. We pass it the initial value. In this case, it's going to be 5. And that's all it needs. And what it gets back is the dispatcher. So now our test should be working the same way. Let me just verify that this refactoring is working before I move forward. I just moved some of the logic to its own function. Let's give it a try. Let's clear this and run the test again. Let's wait a little bit. Okay, so it works. The refactoring didn't affect the code at all. That's good. Aman is asking, can you talk about how Foundry's test runner isn't forged differ from full-blown STRK sequencer? What are the key optimizations it makes to achieve its speed? And what are the trade-offs as a developer should be aware of when writing tests? For example, does it handle parallel execution in the same way as the mainnet? So it's a good question because we are deploying this somewhere, right? Where is this being deployed? And what's happening is that STRK Foundry, it has its own internal like mock version of a STRK. It is not the devnet. Like it is not the thing that starts when we run yarn chain. This is a different devnet, which has much more features, even has an RPC server. So it's more complex. This is not. This is a simpler version only for testing that tries to mock how STRK works. But it's a much more smaller version of it. That's why it's much faster to deploy and to interact with it, because now you don't have all this issue of paying gas fees or mining blocks. It has a lot of simplification just to make testing faster, but it still makes you feel like you're interacting with a blockchain where you can deploy things and you can call. And it comes with a start token pre-deployed as well. We're going to make use of it in a different test. About parallel execution, I don't think it's doing parallel execution. I might be wrong, but maybe that's optimization for future version. Because let me do something quickly to show you how different it is in a newer version of these dependencies. Let me see how I do this. Let me go for a moment. Let me go dev container. Just for a moment, I'm going to switch to 2.12.0. I'm going to get back to it just to not confuse people, but I just want to show you differences in speed. So now I'm at 2.12. And if I open scarp.toml, let me just change this quickly to 2.12 as well. If I verify the dependencies, scarp version 2.12. So if now I run yarn test, I need to solve dependencies again. But does the minimum version? Oh, okay. It needs to be upgraded with 0.48. I'm gonna do this quickly and get back to it, which I think that's the version I have here as well as in Forge version 0.48.1. Try again. So the first time it's a little bit slower because it's gonna cache this value. So the second time should be a little bit faster in theory. And yes, much faster, right? So that is the benefit of using a newer version of, actually I can stay here for now if you don't mind, so we can move faster as well, because the idea of this is have a closer feedback loop from building the feature and make sure that it's working with the test. So again, what I did is I went to dev container. I used the latest one, 2.12.0, but I had to make sure to also go to scrap.toml and use have the same version 2.12.0 here and 0.48.1 because that's the binaries that comes with that Docker image. Hopefully that answered the question. All right, back to the test. Right. We were now testing increase counter, okay? And as I mentioned, you always want to start from a blank slate, so you always want to start by deploying a fresh smart contract to your test scenario. So let's have it here. Let's say that it's 5 again, or maybe just 0 to make it different. Okay. Actually, to be more specific, let's call this let init counter equals u32 equals 0 because we might need this for the test at the end. Just move it out as its own variable to be more explicit. So now I'm going to use the dispatcher to call the function increase counter. Okay. Of course, this is going to give me back nothing. If I see the code, I don't think we return anything. Increase counter doesn't return anything. So after calling it, we need to call the get counter to see what's now the value after doing this. So let's capture this as the current counter. And now we do an expectation, right? So if this is working correctly, after the increment, I should be able to see that the current counter is equals to 1, right? Because start at 0, goes to 1. And if it fails, increase counter function doesn't work, whatever. Simpler message. Let's see. That's all in theory we should be able to do. Let's run our test cases. Let's put it here visible. Oops. Where am I? Terminal. Okay. Yarn test. Okay, so now I have 2 tests running and the 2 of them are passing. That's a good sign, but always you need to see your test fail. So let's see that is 2 and they should fail. And that's right? It's incorrect because it should not be 2, it should be just 1, and it's failing with the error message we define. All good? So we'll bring it back to 1, and it's working. Great. Okay, what else? That's all we can test about this function. We can copy paste the same for decrease counter, it's very similar. Let's call this decrease counter. Let's say that is 1. Maybe a different number. Let's say that is 4. And after calling decrease counter, it obviously should be 3. Let's take a look. Yes, it's passing. We need to see the test fail. So let's say that is the same value just in case. Yeah, it fails, so the test is wired correctly. So when you decrease, you go from 4 to 3. All good. But the error message is incorrect. It will be decrease counter function doesn't work. Okay. Okay, good. What else can we test from decrease counter? Question to the chat. Is this the only test we could do for this function, or is something else we should be able to test here? Any ideas in the chat? This is the function, by the way. I'm talking about this function in particular. We tested one scenario that we can go from 4 to 3. Yes, Ajulo, you're right. We need to test the underflow, right? Because, yes, Emin Ali also, the unhappy path, and Jacobo also, correct? We tested the happy flow, and the happy flow is that the value is greater than 0. In this case, we started with 4 and we went to 3. Well, we need to make sure that when we pass 0, for example, they should fail with a specific error message, right? Because we need to make sure that their underflow protection is actually in place. So let's call this test decrease counter happy path. Let's create a new one. Let's call it the fail path, okay? And the fail path will be, what if we start with the counter at 0 and then we're trying to decrease? So what should happen here is that we will never be able to even reach this section, because at this point, the execution is going to fail and the code basically is going to panic. It's like erasing an error, right? So the way to verify that a test should panic is with a specific attribute that is called should panic. Let me see my notes. I should try doing it right. Should panic, right? Let me remove this because we're never going to hit this. What we test is that it should fail. We don't even need to capture the value. We just need to make sure that when we call it, it should panic. Again, this error is just because there's an issue with some of them, I guess, a process running in the background trying to collect this, but it's working. And to make sure, let's run the test. Let's put this into view. Let's see what happens. If the test passes, it means that it's failing. It's panicking, right? That we're hitting the underflow thing, and it's passing. That is good. That is correct. Because again, let's say the test failed. If I put this to 1, and if I call decrease counter, it should not panic. So it means that the test should fail. And sure enough, we see the test failing in scenario. So it is capturing the right thing, and this is how you test the unhappy path. You can go one step further. You can even verify that it's panicking with the correct error message, because maybe you can check that this is the exact error message that is being displayed when it's panicking. And we can do that by basically extending this with the property expected, and then we pass the error that we expect to see. Let's give it a try. It's passing. So let's make some silly change, blah, right? So if the code doesn't fail with the exact error message, this test is not going to pass. So again, we need to see the test fail. So what it shows is that it's failing. It is showing you that it's actually verifying the error message is the one that is being expected from it. Aman Shaikh is asking, David, what is the proposed carrier structure for handling large integer types like U256 and performing efficient conversions with the native fail type, especially when bridging from L1 or interacting with external contracts? Can you elaborate on it? Handle large integer types and performing efficient conversions with the native fail type. So you're bringing from L1?
Maybe I can.
Or interacting with external. Yeah, Tirth, have an answer?
Yeah, I'll just type it.
Okay, so Truth is gonna type the answer for you. All right, maybe I'll leave you more for you, Truth, to answer some of the questions. But you can tag me if something you want me to answer live, just to not be keep moving forward, because we already have consumed 50 minutes. Okay, we have 1, 2, 3, 4 test scenarios. Okay, so we tested, in this case, the happy path, the unhappy path. Well, there's something else we should be able to test that we are not testing. What is it? A question for you in the chat. What else can we test here? in the decrease counter, but also in the increase counter, something that we forgot to verify as well. Any ideas in the chat? There's no ideas. Yes, I mean, that's exactly. We are not verifying that we're getting the right events, and the right event is being emitted when we make a change. So we need to make sure that as well. And that was a limitation when trying to do the manual testing using the web UI, because there was no way to see the events. But now in Foundry, we actually can test that. So let's go back to the increase counter first, because both have. And what I'm going to do is right when I deploy, I'm going to start what is called a spy. And a spy is basically is to capture any event. It's called spy events. And that's going to come from Foundry as in Forge. So do I need this? Oh, yeah. Let's put it here. Declare result. Oops. Declare result thread. And I want to add the spy events. What's going on? Is defined multiple times. Why? Oh, because it was added here. Okay, spy events. So spy events, this is gonna start the spying, all the events raised from this point on. So we're gonna capture whatever was spy in a variable called spy. Okay. So now that we have the spy, what we could do is after we call the counter at this point, and the event should be raised, so the spy should be able to capture that event. So let's build our first of all, this is the expected. Let's build the expected event. So let expected event, and let's build the event ourselves. So the event we want to build is obviously the one defined here, the counter. We want to build this, the counter changed. In order to bring it into scope, we need to make this public. And we will need to make this also public because it's part also the same struct. Okay, so let's back here. Let's bring that into scope. And it's gonna be in the, is it here? I think I need to go one level deeper. Use contracts, contract. I have to enter here. Counter change. It's not visible in this context. Oh, okay. What's complaining is, again, this module is not visible outside of it because it needs to be made public first. So now that it's public, we should be able to reach out to it. And now we have access to the counter change struct that we can use to create our event. So counter change, this is a struct, and now we define the values. And it is expecting to be passed. We have color, old value, and reason, right? You have all these things. So let's start with the color, old value, and new value. So color, and the color, who's the one calling the contract right now? It's going to be the owner. Wait a second, who's calling this? User address. Okay, I see. So the one thing is that it's unclear right now who's going to be the role of the caller in a test, right? Because we're doing a test scenario. So what is our address? We don't have one. So in order to mock an address, we need to use what's called cheat code. Let me show you how it works. So before we call the increase counter, we're gonna add a cheat code that is called start cheat account start cheat caller address. And this is gonna like make pretend that we're calling this smart contract from a specific address. So now we can come here and start cheat account contract. No, cheat account caller address. And this thing is expecting to be passed. So first of all, which contract do you want to mock or to fool with this? And the one we want to fool is actually the counter contract, right? And we can get it from counter, deploy counter. Give me 1 second. Dispatcher address. Yes. So from dispatcher, we can get the address that it was deployed. So say we're going to fool this particular address, which is the one that we're calling here. And we're going to fool by making it pretend that we're calling from being certain user. So let's make the same trick that we did here, right? This is how we trick into creating like a fake address. I'm actually going to create a couple of functions that we can reuse. Call this like a user address. And let's use for the user owner so we can move this out. So when I call this, I get back is a contract address. And it's basically going to do this. Right? So we can use this function instead. User, sorry, this is called owner address. Owner address, let's call this the owner address function. And we do the same, but now for a different address that we're going to call just user. So we have like two different addresses to play with. And we change the field. Okay, so whenever we want to get the address from a fake user that we're going to pretend to be, we're going to call this function. And this is going to be a function for getting the address of the owner. So now I can use here, like give me the user address. Let's pretend that this is our address now. And we need to start the cheat. We don't want this to go on forever. So we bring another function. It's called stop cheat caller address. Cheat caller address. We can start and we can stop. Bring this down. Okay, so we start here and we can stop here. Stop cheat caller address. And that's all we need. Do we need to pass anything? We need to pass the contract address again. So this is the one we're trying to fool. There you go. So what's happening now here is that whenever we call this increase counter, the method get caller address inside this function is going to give you back whatever we pass here, the user address. So whenever this is called, and we can see that it's just in the event. So now when this function is being called, what is being returned is the user address. So now we have certainty what is going to be provided here in the caller. So we go back in the now we can actually mock the event. So we know that the caller is the user address. And we know that the old value is going to be 0, right? The initial counter. Or maybe we can just make it explicit. And then the new value, it's going to be, well, make it simple, 0 to 1. And then we have to pass now the reason. The reason, again, is an enum that we need to bring into scope. So we need to make it public. Change reason is public. So we can bring here counter change, but also reason, change reason. So we bring both. So now I can say change reason dot, and I need to actually export every member to be able to access them. I think it's this. Publish a reserve identifier. It's not this change. Let me try this again. What am I doing here? Change reason. Expect available customer. Okay, so this is the increase. Oh, apparently I don't have to import. Let me see. Something is not working here. Member color is not visible in this context. Okay, so what I have to make public is these properties. Otherwise, they're not visible outside. So not only the struct, but each property as well. And now this is apparently working. Until here, expected variable or constant found type. Why is this? Let me see my notes. What am I doing wrong? Oh, it's because this is not the syntax. The syntax is the double colons. That's how we access the member of the enum. Okay, so this is what we expect the event to be. But now the question is, what was the real event that was emitted? So to make that check, we can go access the spy that we define here. And then we call the function assert emitted. And we pass it basically an array. And use the macro here. And this is gonna be a tuple. It's gonna be who is raising the event. In this case, is the dispatcher, the contract address, who's raising the event, and what is the event that we're expecting. So we create the event counter changed, and then we have expected event. This is failing because I think we need to make this public as well. We need to bring it into scope. Event not visible. Where's this coming from? Let me double check for a moment. Event, it should be here. Counter contract. Oh, it's not visible because, again, we need to make this public. Let's try it. So now it's visible. I can bring it into scope and I can use it. To summarize, so the expectation is that a particular smart contract address, in this case, the one that we created, is raising this particular event, right? The one that we define here. So let's see, let's run the test. It's passing. Again, we need to see the test fail. What if we make this to be true, right? So this should make the test fail if this spy is really working. And indeed, it is working because the test is failing. So we're back to 1. And we can use the same logic basically for the decrease counter, the happy path, because now it will be from 4 to 3, and the change region will be decrease. And we need to start the spy event as we did before. Oops. No, the spy event, where are you? I'll make the spy here. And we need to do the cheat code. So the right address is being captured. So before we call the method decrease counter, we start the cheat code and we stop the cheat code right here. We don't need to cheat the get counter because in the get counter, we never call the function get caller address. So that's fine to leave it out. You can leave it in if you want. It doesn't make a difference. So let's see if this is working now. Yep. All right. So we have multiple tests that we have covered. Happy path, the fail path. We are testing events. We are using cheat codes. And we are in a good spot to have a break. Right. So we have tested so far. We have tested the functions get counter, increase counter with the event included, decrease counter, happy path, failure path, event included. We can now move on to set counter, which is going to be fairly similar to what we've done before. The only thing here to keep in mind is that this function would fail or will only execute if the owner of the contract is the one calling it. Any other person calling it will make the function fail. We need to test the function being called by a user and by the owner. So let's go to the test scenario. All right. Let's start with the happy path. And let's call this function Let me see what name I get it. Okay. Function test set counter owner, right? This is the happy path. We usually, or as always, we start by deploying the smart contract to our instance. Let's start with a different number because we're going to reset. Let's say that is 8. And we are also going to, let me see, let's call the dispatcher reset counter. But the thing is, we're going to have to use a cheat code to pretend that we're calling this method while being the owner, right? And not just the user. So we go to our cheat codes. We need this one. And instead of being the user address, I'm going to put the owner address. Okay, so this is the happy path. And then we stop this cheat code. Stop. Okay. So now, if this is working, we should do an assertion. And being that, if I call get counter, I should get 0, right? The owner, if it fails, it means that the owner is unable to reset the counter. Okay, this is the happy path. Let's see if it's everything correctly. Reset the counter, go from 8, go to 0. Let's give it a try. Test. Ooh, okay. I'm using the wrong function. It's called set counter. Sorry. Set counter. Yeah, reset counter works differently. Why is this? Oh, because we set the counter to a specific value. Oh, okay. Let's put it here. New counter. Let's say that this is the value. They're going to set this to 15, let's say. So I'm going to set this to this value. And now what we expect is to be set to the value. Let's try again. Okay. Tests are passing. So the happy path is working. We can also test the event, right? Because if this goes through, we should be seeing this event. So let's put it here. Let's call this the expected event. And it should start with 8 and go all the way to, maybe I can just use the variables from here to here. And the color should be the owner, right? Because that's what we're mocking here. And the reason should be set. So that is correct. So now let's do the assertion of the event as before. It's the same. And we need to spy the event. Start the spy with this line. Okay, start spying. Good. Let's see it again. Let's see the test fail. Let's see that this is now 0. It's before. This should fail. Correct, it's failing, so it's fine. And let's see this one fail. Let the event. That's right. So we make sure that we're not getting false positives. Everything's working correctly. We can go now for the failing path, and the failing path will be to call set counter as a user or as a non-owner. Let's call this new scenario function test set counter non-owner. So the test is going to start the same way. We don't need to spy because it should fail. Oh, and because it should fail, we should define that expectation here should panic in this case. I don't put a specific error message because when this panics, it's because of this method that is part of the component from OpenZeppelin. So I don't know exactly what the OpenZeppelin is, what message is throwing. So I'm not going to try to catch the specific message, just that it's panicking. It starts the same way. We deploy. We don't need to spy this point, but we need to try to call the method. But to make it fail, we're going to call it as the user. So at this point, actually, I will never even reach this line. We just panic here. So let's give it a try. This should pass the test because it should fail because it's the user, which is not the owner, trying to call the method. It is working fine, right? Again, if I switch this to owner, I need to see the test fail. There you go. Back to user, all good. And that's all the test scenarios for set counter. Now we go with maybe the most difficult one to test, the reset counter. There's a lot going on here, right? Because the reset counter, anyone can call it, but you have to pay specific amount, in this case, 1 STRK token, to be able to set reset the value, and that amount is actually being paid to the owner of the smart contract. So we need to define all these things. So let's start maybe with the happy path, as usually. So test, in this case, is the reset counter. Let's call it, what is the easiest one to test first? Okay, enough balance. This is harder to test. Let me try. So the happy path, the first one to test would be set counter and sufficient balance. Let's say that you don't have enough STRK tokens, right? So we know that this should fail. This is a function. So if you don't have insufficient balance, this should fail, should panic. And this should panic with a specific error message. The one we're trying to capture here will be user doesn't have enough balance. So let's try to set up this scenario. We can start the same, some value, let's say this 8, whatever. We deploy the smart contract. Now we want to call function set counter. No, sorry, again, reset counter. And do we need to mock? I think it's better to mock who's calling it so we can catch the event with the right value for caller. Let's say that we call it as a user. And we stop here right after. Okay, well, it's not going to get here because it will fail here, because if we don't do anything here in the test, in the setup phase, it means that the user doesn't have any STRK token. It starts with 0. Okay, so this should fail. And let's verify. And by failing, I mean it should panic with this error message, so the test will pass. That's what I'm trying to say, which is correct, right? Because the user doesn't have enough money. Doesn't have, I think it's 1 STRK that we are requiring. Test number 1. Now, test number 2 will be, what if the user has enough balance, but has not given enough allowance to the smart contract to withdraw for the user? So that's scenario number 2. So I'm going to copy these 2 things. The error message we should now expect to see is this one. Contract is not allowed to spend STRK, so it doesn't have enough allowance. In the function test, reset counter, insufficient allowance. Okay. We start again. We initialize the smart contract. We deploy it. But now we need to find a way to give it a STRK tokens to the user. Not the allowance, but at least some STRK tokens to the scenario is you have enough balance, but not enough allowance. There's multiple ways to do this. There's actually the STRK Foundry has a function specifically for this method, because in this testing engine, there's a start token being deployed that you can actually control and just give tokens to whoever you want. And you can do that with a function called setBalance. Okay. We need a couple of things. We need to, first of all, bring this function into scope. So it should be part of the testing suite of SMForge, setBalance. Okay, we go back here. So setBalance is expecting to be passed the contract address, that the person that's going to get the tokens, what's going to be the new balance we want to give it, and which token, because there is there's an ERC20 for ETH, there's an ERC20 for STRK, so you can mock both of them. Okay, let's, obviously the user, let's call here, let caller user address, more explicit. So I'm gonna set the balance for the caller. I'm gonna set how much. Let's give it at 10 star tokens. And again, it's a 10 followed by 18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If we have time, we can create a small function to make this a little bit easier. You pass the whole number, just give it all the decimals. And finally, which token? And the token is an enum. So I guess I need to bring this enum into scope as well. Token, yes. So there should be two different tokens. Token, it could be either STRK or ETH. So I want to now give it to ETH. Okay, so at this point, the user should have 10 star tokens in their balance, but not allowance yet for the smart contract. So even at this point, if we try to call the function, let's just here call it, just to avoid calling the function multiple times. This should also fail, but it should fail now with this error message, right? Because it should be able to pass this verification, but not this verification. So let's give it a try. Yes, it is passing. Now we need to say the test failed. What if we give it not enough balance? Let's remove 2 zeros. They should also fail, but with this error message, right? So it makes this test not passed, because now the user doesn't have enough balance. It doesn't get even to the allowance part, and that's correct. Okay, so we saw it fail. We know it's wired correctly. Great, that's test scenario number 2. What else? What if it has enough balance and it has enough allowance, right? So the next step, how do we give it allowance to the user, or to the smart contract to withdraw for the user? So one thing to keep in mind is that we need to know what is the address of the ERC20 token that represents the STRK. And I mentioned that it's always the same in any scenario, in mainnet, in testnet, in devnet, even here in Foundry as well. The address is always the same. And that address is, we actually have it in the counter. We actually hard-coded that here, right? So what I'm going to do is I'm going to move this, because we're going to need this address as well for the test. I'm going to move it to its own util function, so we can consume it both in the smart contract and in the test. So for this, I'm going to create here a new file. Let's call this utils.cairo. And I'm going to create a function called STRK address, which is going to return contract address. And of course, we need to bring contract address into scope. Contract address. And it's going to return this value right here. It's going to do basically exactly this without the semicolon. So it returns the value We're gonna make this public so we can export it, and we need to go to our main entry point and define this as a module utils. So now that is visible in the counter, so I can actually bring it into scope. I can bring it into scope here. I can use, how do I call it? Counter? No, contracts. Contracts, and then utils, and then the function STRK address. Bring that into scope. I can replace this one here. STRK address. What is this complaining? Variable not drop. Trading has no implementation. That is confusing. What is doing this? Just bringing the STRK address. That is strange. What is complaining about this? Trade has no implementation in context for trade drop. Missing the struct, pending the struct, variable not drop. Oh wait, what's happening? The tab is not found. Am I making a mistake here? Start. I think, using the use statement. Yes, that should fix this. Okay, cool. So now that I have the function, I actually use it in the test as well. So I can bring it into scope. Same way. Contracts. Utils. STRK address. Okay, I have the STRK address. So what else I need to do? Let me see my notes. In my notes I have. Okay, cool. So we start as before, insufficient allowance. Okay, let's start a new test scenario. This is going to be a happy path, so they should not fail. Function, test, reset, counter, success. It starts the same way. We're going to make it as the user. We're going to give it enough balance as well. But now we need to make a way to give it, to do the allowance. So for that, we actually need to use the dispatcher for the ERC20 token and call the approve method on the token. So for that, we need to bring the dispatcher from OpenZeppelin, the dispatcher for the ERC20. So use OpenZeppelin token, the ERC20, and we're gonna bring the dispatcher here. What's the term? Oh, we need to bring interface, and from here we're gonna bring the ERC20 dispatcher and the trait. Dispatcher trait. Okay, so we can call the methods. So this is going from ERC20 from the OpenZeppelin. We know the address. So in theory, now we should be able to see, let me see my notes again. Okay, let's say ERC20 is going to be equal. So let's call the dispatcher that we bring to scope ERC20 dispatcher. This is expecting the contract address, which is going to be the one that we're calling from the function, the STRK address. And what's happening here? And this is a function. Okay, so that should give us back a dispatcher to interact with the ERC20 token. Then now we should be able to call the method approve. And we need to give it how much to approve. So it's expected, who's going to be the spender? In this case, it's going to be the address of the counter contract and how much. And we need to, okay, right. So before we call this method, we need to call it as the user, because only the user is the one who can approve this. So we need to start cheating the cheat code. I'm gonna call this user. Maybe it's more descriptive. User. So now the user is calling this smart contract. I'm gonna stop the cheating here. Stop. And now I can give it, I need to know, let's call this, so it needs to know the address who, okay. So dispatcher, because we have multiple dispatcher. Here is ambiguous called dispatcher. We're just gonna call this the contract, the counter. Counter, because now I have two dispatcher, one for ES20, one from the counter. So counter.address, some contract address. And how much? Let's give it that it can spend 5 STRK. So it's a 5 followed by 18 zeros. So let's put 5. And that should give it enough allowance. So let's, oh, okay, there's a mistake here. When I'm doing the cheat code, I want to do the cheat code for the ERC20 token, not for the counter here. So this is the one I'm trying to fool, basically. So it has the wrong dispatcher. Let's see. So at some point, in theory, you should have enough balance and enough allowance to now be able to call it. I call this counter. Call this now user. Call this counter. So now I call it the reset counter. I should stop this cheat code stop. And this should be the happy path, right? So at this point, I should be able to do an assertion in saying that counter.getCounter should be equal to 0. And if not, it means that unable to reset counter even with money, even with enough STRK. Let's see, this is a complex one. This could actually fail. Let's give it a try. Oh, it passed. Wow. Okay. Let's see it fail. How do I can make it see it fail? What if we don't give it enough allowance? I'm just gonna remove 1 0 from here. So instead of having 5 STRK tokens, it's half STRK token. Should make the test fail. Yes. Yes, 1 failed. Okay. So this is working. Back to normal. And because the happy path, we also need to check that the right error the right event is being raised. So let's do the same trick as before. We're gonna define an expected event. We're gonna spy on it. And we know the initial counter will be 8. New counter will be 0. The color should be we call it the user. And the change resource will be reset. And we need to start the spy here. Let's copy this. And we're going to spy everything, not just like for both smart contracts. That's why we need to define which event we want to assess, the event of which contract we want to do the assessment, in this case for the counter. Let's run this again to see if the event assertion is working. Yes, let's see the test fail. Let's say that it's failed for a different reason. Let's say that it's decrease. Yes. Okay. So the event is being emitted. the assertion is working. Maybe the final check is that the balance is being updated correctly. Because if this is working, what should happen is that the balance of the user should have decreased by 1, and the balance of the owner should increase by 1. So we can do this assertion. How do we call this? Let's see. We can call the ERC20 token the dispatcher, and we call the function balance of. So I see the balance of the user. It is expects to pass. So the address, let's first go the user. So this balance should be assert. So it should be 9, right? It was 10 before, now it should be 9, but with the 8, all the zeros that we need. And 9. Balance not updated correctly. Let's see. So it should be paid 1 star token, which is what we're asking here to be paid. Yes. Let's modify here the value to see the test fail. Yes, see it fail. That's working well. And I could go on. One final test is that the owner should now have 1 star token. So we can do very similar. Just instead of the balance of the user, let's get the balance of the owner. In this case, it's called the owner address. And it should be 1, the payment. Balance not deducted correctly and balance not increased correctly. And this should be the final test of our testing suite. This should be ending the session. Yes. All right. So we check. This is a more complex one, because not only we had to set the balance, we had to define the allowance, and then we call the reset. We check the counter is updated. We check the event is the correct one emitted, and then we check that the balances are updated correctly as well. One thing to do here, maybe I can do it quickly, is this is very, very hard to read. 9, a bunch of zeros. You can create a utility function. Here, for example, maybe I don't have 15 minutes left. Maybe I don't have time. Let's create this utility function. Let's call this, let me see my notes. Okay. STRK to fry. Because actually, the smallest number on STRK is actually called fry, not way. So it's going to be passed, expect a whole number to be passed. So let's call the amount as U256. So you can define a large amount. And it's going to return another U256, now with the 18 zeros associated with it. I'm going to make this is a function. I'm going to make this one mutable. And what I'm going to do is, first of all, define how many decimals. In the decimals is 18 decimals, as we know. And let's define a variable to iterate. A small variable, U8, start with 0. And then we use a while loop. Go from I. So while I is different from decimals, so what we're going to do is take the amount and we multiply it by 10. Right? So this is adding, oops. What is happening here? Amount. I need to initialize, have amount here. What is the amount? Invalid left-handed side of assignment. Why? Amount, what am I doing wrong? Oh, mount, missing an N. Okay, and increase the iterator by 1. So you should iterate this 18 times, every time adding 1 0 until I get 18 zeros. And at the end, I return the final amount. So this turning, for example, if I pass 10, I should get back 18, right? And we can actually create a test here. In this case, a unit test. CFG test. Mod tests. And we define a function test STRK fry. This is a unit test. In this case, I'm just going to call start to fry. If I pass it 10, I should be able to get 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Expecting Boolean. So what am I doing wrong here? Okay, this is equal. Oh, yes, it's an equality. I'm not going to put an error message. So let's test this. So Foundry should be able to run both the integration test and the unit test. All right, let's see it fail again. Let's miss 1 0. Yes, so it's working. So I can now replace. I use this function in different places. Like for example, instead of doing here like this, let me bring this into scope. So I'm bringing 2 things from this module. Start to fry as well. And now I can use it. So it's more readable. Start to fry, so with 10. And we do the same for the test scenario. You can use this everywhere. You need to bring it into scope. Start to fry. Now, anytime we have these long numbers, you can use that instead. So much easier to read. Start to fry. We're passing here was 10 STRK, if I'm not mistaken. With one as well. Start to fry. This was 10 as well. This one here is 5. And we checking the balance as well. This was 9. And the final one was 1. Okay, the moment of truth. Let's try running this again. Something failed. What is failing? Contract is not allowed to spend enough STRK, and that is the reset counter success. Reset counter success. And the failure says contract is not allowed to spend enough start. Right, so it's not passing. This one. So the allowance is failing. Why is that? It says here. This approve is not working correctly. Any idea what's happening here? So this is something about the function itself. Start to fry, give it 10 for balance, give it 5 for allowance. Did I make the test correctly? Ten. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Let's say maybe use contract util start to fry. Contracts utils start to fry. It's here. Let me put a large number just in case. What if I give it like 150 just to see if maybe it's just decimals being wrong. Balance not deducted correctly. Oh, wait, I think I know why. I modify the payment amount should be 1, not 10. That is the issue. So I just inadvertently use the wrong number of decimals. 10, 5. This should work now. Yes. There you have it. We did a lot today in testing. We're testing all the scenarios, failing scenarios, should panic, expected error messages. We use cheat codes to mock some addresses on callers. We spy events. We interacted with the start token to set a balance, to do allowance, and then to verify things change as we expected.